Well, greetings, mathletes, and welcome back. So we're going to continue talking about isometries today, and the one we're talking about is going to be rotations. Now, rotations are basically exactly what it sounds like. It's something rotating, but most of the time what you picture in your head when you talk about rotations is something rotating and about its own center, right? So something turning like this, but it doesn't have to be that. All there really needs to be is a center. It doesn't have to be inside the figure, and an angle of rotation. So let's take a look at an actual graphic of this so we can kind of get an idea of what's going on. So here's what I've set up here. This is the shape. This is the one that we're going to be rotating. And the rotation is at this point here in the middle of it. This over here is our angle of rotation. So notice as I change this, it rotates around that point that I have there. So as this angle changes, the angle that it's rotating changes. Okay, so that's pretty straightforward. When it gets a little weird is when you move the point of the center of rotation outside of the figure. What you start ending up with is something that rotates. Oh, I grabbed the wrong one. I meant to grab this one. There we go. Something that rotates um, around. It's kind of an orbit, really. You notice it doesn't matter whether I change the length of this side. It's only the angle that it's measuring, right? So you can end up, if you make the angle 0, you can line it back up with the original thing, right? But as soon as you change that angle to non-zero, it moves off of it. And everything changes according to where the center actually is, because it's going to rotate about whatever point you have designated as the center. Okay, so that's the idea, and you can kind of see the rotation here. As a matter of fact, probably makes the rotation a little more clear if I do something like this. Let's just put that right on there. Now watch the rotation. Oh, that's the circle tools. Oops. Try it again. There we go. If I take this angle of rotation, you can see it's moving around that center on the circle. And just for the record, that is also going to set up the fact that we can do this with compass and straight edge as well. Okay, so let's go ahead and jump back here. All right. And what we're going to do here is we're actually going to take a look at how to do this with dot paper, how to do this with a compass and straight edge, and then how to do this using coordinates, right? How do you transform your coordinates? The same way we did with translations, right? With translations, you add something. With rotations, it's a little bit different. So now with the dot paper and with the coordinates, we're really going to be focusing on 90-degree rotations and 180-degree rotations. And then the compass and straight edge will be able to actually handle any angle of rotation. In fact, you don't even have to know what the measurement of the angle is. You just have to be able to copy it. Okay, so having said that, let's go ahead and get started here. Let's get that focused. I'm going to apologize for the condition of my left hand. I own a cat, and the cat has owned me. And anyways, we were wrestling last night, and she left some marks on my hands. So just letting you know ahead of time that. Okay. Okay. So the first thing we want to do now, these are all of our givens here. This is our original shape, this is our center, and this is our angle of rotation, which is 90 degrees in this case. Okay, so we're going to try to rotate this point 90 degrees around this center, right? Just like we saw in the computer graphic, except we're going to be doing this, with the dot paper. Okay, so here's how I like to handle things. So you can see from here, right, we have a line. Now I'm going to be putting all of the construction stuff in red, and then I'm going to put the final product of rotation in blue. So you can see which things are used for construction and which things are the final product, and all that kind of good stuff. Okay, so this has to rotate 90 degrees, right, from this angle. So that means I need a 90-degree angle off of this. So I'm actually going to look at this here, And I can see from horizontal, this I move 1, 2, 3, 4 over and 1 up, right? So now to get a 90 degrees, I'm going to move 1, 2, 3, 4 up and 1 over. So I'm actually kind of using the slope to figure out 90 degrees, right? And what I'm actually looking at is this. The rise and run here, I need to mirror it over here. That's actually what I'm doing. So I'm looking at these four. Now these are vertical. And this one that goes up, once it's rotated, is going to go that way, right? Because it has that rotation in this direction. Okay. Unless you're told otherwise, all rotations are counterclockwise. Okay, so we have a 90-degree angle here, and we need to make sure it's at the same distance, and that's another reason we could count that off. And so that should be this point here. Okay, now we're going to do this with each point. So that's my second line here, and I need 90 degrees from that and the same distance. So that's going to go this direction. And there's my second point. So notice what happened. This horizontal side is now a vertical side, right? I can actually draw that side in. So this is my first point. Here's my second point. If I connect the dots there, I get my first side, right? So this side is the same as this side. Now we just need to figure out where that last point is. So we're going to do the exact same thing. We'll get our line here, and then we'll copy it at a 90-degree angle. So this slope here, let's see, I count 1, 2, 3, 4 up and 3 over. So if I rotate that 90 degrees, I'm going to count, wait, 4 up, yeah, 4 up and 3 to the right. So if I rotate this 90 degrees, let's see here, that will be 4, 1, 2, 3, 4 to the left and 3 up. So that puts it right here. And that should be at a 90-degree angle to this side. And you can see, right, that it is a 90-degree angle. So now that I have my last point, oops, that's the wrong color. Well, this will be multicolored. Be like Joseph's coat. There we go. And there we go. Right, so now with the rotation, this side matches this side, right? It rotated. This side matches this side, and then our last side here matches this last side, right? You can see it rotated this way. And that was a lot of little lines there, but it's just a matter of finding right angles from the center of rotation. So you draw the point you want to turn, you draw a line from the center of rotation to that point, and if you were constructing this, you would construct a right angle and then measure off that distance so that it's the same as this distance. There it is, right? So those are the things that you want to get done here. And that's doing it from the dot paper. If you wanted to turn 180 degrees, it's the same thing. It's just you're going another 90 degrees after that. So that one's not too bad. Okay, so let's say we wanted to rotate this one. So we have a center here, right? And this is our figure. And this is down here is the angle that we want to rotate. Remember, all rotations, unless otherwise noted, are counterclockwise, right? It just in math, that is considered the positive direction when you're measuring angles. If you measure in the other direction, it's considered the negative direction. So that means we're taking this thing and it's going to rotate this way, right? So it's going to go this way somehow. Oop, let's draw it so you can see it. It's going to go this way somehow, right? Okay, so let's go ahead and do this. So basically what I need to do is start with the center. I'm going to actually pick this farthest point first to do. But yeah, you draw a line between the center and the point you want to rotate. Then what we're going to do is copy this angle here, right? So this angle down here, I'm going to copy here so I can see how far to rotate it. And then I'll remeasure this distance because it needs to be the same distance and figure out how far it needs to be on that distance. So let's copy the angle first. Oh yeah, I need my compass here. Let's get, there we go. So I got my compass. We just need to copy this here angle. So let's do this. Okay, so we'll do that here. Okay, so we got that first mark. Yeah, and then we just need the second mark. Let's go ahead and, nope, too big. Why is that? Pretty close. Okay, so let's measure it here. Okay, so we have the angle measured. I'm going to draw that in now. That's going to go from here to here. Now we need to go out. Oop, we need to go out far enough so I can measure off the proper distance. There we go. And then we just need to figure out how far this point is from here and then copy that distance over here. There you can see my cat tore my hand up pretty good last night. It's okay. We like to wrestle. She just usually doesn't get that violent about it. There, I think that's better. Okay, so we just need to copy that over. Okay, so put that in blue. So there's my first point, right? So I've just rotated that. Now I just need to rotate the other two. So I'm going to do this one next. Okay, so same business. I need to draw my line through and make it long enough so that I can copy the angle down here. Okay, so I need to copy this angle again, which means I got to do a whole bunch of stuff over. So let's just copy that arc. Do it again. Is it big enough? Just. Okay, and then we'll just close this up. There we go. Nope, not enough. There we go. And I just need to measure that from here. Oh, I didn't make the first one long enough. Let's do it again. Sorry if you can't see it. There we go. All right, now I got a crossing. Okay, so this, oh, actually that should be, that's not a final point. That should be in red. That is going to give me my next angle. And remember, we were copying this point. So what that means is now I need to measure that point's distance. There we go, and just copy it. Now I have a second point, so I have 2 points now. That's this and this. So now we just need the third point, which is looks like it may be inside the original triangle. We'll have to see how that plays out. So we've copied 2 points so far. We just need that third. And you notice one of the issues here is keeping track of what marks mean what, right? That actually ends up being kind of a big deal. So let's do this one more time. Okay. All right, I just need to copy this distance now. Actually, I was noticing we probably could have done all of them at once if we had been clever enough, but we're not. Well, I'm not. Okay. And then that should be my last angle copy. Okay, so this is the one, right? That's the one we're working on. We just need this distance copied here. So we're going to do that. And here, oh my goodness, is that the right distance? I'll be damned. All right, so that's my last one there. And now I should be able to connect the 3 blue dots and have a copy, a rotated copy of this original triangle. And you can see that this can become very, very tedious, right? So we've just taken this black triangle and rotated it to this blue triangle. As a matter of fact, let's go ahead and bold those up a little bit so we can see what our finish and ending products actually were a little bit better. There we go. Or finish and ending. Our beginning and ending. Well, I was talking about people from Finland, because they're Finnish. I don't know. I'm just trying. I'm looking for something here. It's probably not a joke I should have bothered with because it's not funny. But that's never stopped me before. Okay, so that's a little more, a little clearer depiction of what has actually happened. Basically, what we did, we took each point and then copied this angle and then figured out where the point had to rotate to under that angle. So we ended up copying 3 different angles one angle 3 times is what we ended up doing. So it's really kind of interesting. You notice there's 3 circles here, right? All centered here. I probably could have started with that. Now I'm thinking about it, it would have made it a lot easier if I had just done the smaller circle drawn a circle through each one of these first and then copied the angle. So really, these are time-saving things that experience tells you. You start to realize there's quicker ways to do things. So in any case, that is how you that is how you rotate a figure using a compass and a straight edge. And so now the next thing we need to do is go ahead and, oh wow. Okay, anyway, sorry, I started thinking about something else. We'll go ahead and look at what happens to coordinates with these things. So let's go ahead and get this off. We'll go back. Oh, that's not dot paper. There we go. I knew I had dot paper in here somewhere. There we are. Okay. Okay, so rotations using coordinates here. Okay, so you could dice out a coordinate on this if you wanted to, but I'm going to keep it generic, so it's just A and B. Um, and let's say we wanted to rotate this. We wanted to rotate it 90 degrees about the origin. And when they say the center of rotation, they say that you rotate it about that point, right? About does mean around. So in any case, the origin is right there. That's the point 0, 0 on your graph, in case you weren't clear on that. So whenever you're asked to rotate as far as coordinates go, there actually ends up being an algebraic way to do this, but you have to understand why it works. Okay, so first, if we're going to take this point and rotate it 90 degrees, that means it's going to, how do I want to write this? It's going to rotate this direction, right? It's going counterclockwise. 90 degrees is a right angle. And conveniently, the axes already make a right angle. Actually, let me do this part in red. Right? So 90 degrees, if I go ahead and measure this thing out, right, I can tease out a slope with it. If I rotate it 90 degrees, that means that this horizontal line will be on here, which means this vertical line will now be this way, and this or this distance will be here. And from those two things, since this is a right triangle, you can actually just copy the triangle up here. So if I look at this, I'll point out that this side length right here, this x coordinate is A, right? That's the length here. And then over here, this height is B. So when I rotate now, one, two, right? I'm going, this height is now A, and this distance right here, this is now negative B, right? Because it's going B to the left of the y-axis. So we end up with this angle over here, and our point that we want is right here, right? Now I want to point some things out. So this started with the coordinate AB. A 90-degree rotation ends up always doing this. And you notice we didn't pick any numbers, right? We just used variables. And so that means that this works no matter what numbers you pick. The coordinates here now are, let me write it in blue. Let's see, the x coordinate is now negative B. And the y coordinate, how tall it is now A. Right? So that gives us something. Do I have something that'll write bigger? This will work. Okay, so for a 90-degree rotation, about the origin, for coordinates, it looks like this. If you start with the point AB, it turns into the point negative B, A. Now, I want to point something else out. One of the things that does usually come up in an algebra course is the fact that when slopes are perpendicular, when lines are perpendicular, their slopes are negative reciprocals of each other. If you look at this, right, what's the slope here? Over here, the slope, let's see, its rise over run is B over A, right? Over here, though, the slope, let's see, its rise over run, it's A over negative B, right? And those are opposite reciprocals of each other. So this is actually a proof for why why perpendicular slopes are negative reciprocals of each other. You can actually just do it with the coordinates. But nonetheless, this is the transformation that you want to be thinking about, right? The fact that, excuse me, the coordinates swap places and the x coordinate changes sign. Okay, so keep that in mind. Now we're going to look at one more of these, and I might reference this page again. Let's see. Oh, good, I still have more dot paper. Okay, so I'm going to save you the construction montage, and we'll have this magical. Okay, so what we're going to look at now is a 180-degree turn, sometimes called a half turn, right? Because you're not turning all the way around. If you turned all the way around, you'd be facing the same direction. So basically, this is going to be rotating this way, right? And this is my center, is going to be the origin. Okay, well, what's nice about this, it's just a matter of, I mean, honestly, it's just a straight line thing. If it's a 180-degree turn, that is a straight angle. And so I should be able to draw this out. If we look at this thing, right? That means the height here is B. This is A. This is B. Let's look at how it plays out. So I should have negative A, right? And then negative B. So that means that the coordinates down here are negative A, negative B. And notice what happened. And this actually turns out to be the case with all 180 terms, with all half turns. 180-degree turn is the coordinate transformation from AB to negative A, negative B. All right, so 90-degree turn goes from AB to negative BA, right? So those are two different things. What would be interesting is if you can see if you can piece together show that two 90-degree turns is the same as a 180-degree turn using just these. It's actually quite useful. But in any case, that is the last thing I wanted to cover, was just how to transform those things as far as the coordinates go. And yeah, there's actually two isometries left. There's a reflection, right, which is actually, instead of rotating something this way, it's flipping it over, right? So you're looking at, it's a mirror image, basically. And then the last thing is what's called a glide reflection, which is a combination of a translation and a reflection. Those oftentimes footprints are used because, you know, feet are mirror image of each other, but they're offset, right? In fact, there's a glide reflection right there, my hands, right? They're reflections of each other, but they've been translated also, right? So this hand flipped over to here to become right. I mirrored this way, and then I offset it, and so now that's what a glide reflection looks like. And in any case, we are going to be taking a look at those, and just not today. In any case, until next time, folks, keep your pencils and your wits sharp, and don't let your compass drift too much.